All right. So at this time, we are getting ready to have our special guest speaker. And to bring him up, I am going to introduce Dr. Ishfaq Ahmad, who will be introducing our speaker. So our talk today, we've titled it Bright Light, Computing Then, Now, and To Be. And it celebrates our connection to industry and to technology. Okay? So let me introduce Dr. Ahmad, who will come up. So Dr. Ishfaq Ahmad is a fellow of IEEE. He's a professor in computer science engineering here at UTA, and he joined in 2002. He earned his PhD in computer science and his MS in computer engineering from Syracuse University. And he's authored about 300 publications, including books and peer-reviewed research papers on supercomputing systems, parallel optimization algorithms, digital video compression, assistive technologies, and sustainable computing. Dr. Ahmad has received more than 30 international research awards, and Google Scholar shows his research papers as highly cited, ranking him among the top 10 researchers in several sub-branches of computer science. Currently, he's also editor-in-chief of Springer's Discover Internet of Things, and he's the author of The Perfect Human, a biography of Muhammad the Prophet. And now we welcome to the stage Dr. Ishfaq Ahmad to introduce our keynote.
Thank you, Dr. Carter. Good afternoon. Dear colleagues, dear students, and dear distinguished guests, I am privileged to introduce today's highly distinguished researcher, Professor Jack Dongarra from the University of Tennessee at Knoxville. Let me start off by saying deep thanks to our guest because he is highly sought after. Dr. Dongarra is very, very busy and he travels all over the world, not just for entertainment, but he's actually working, which is quite intriguing how he accomplishes that. So I wish to say real thanks for gracing this momentous occasion with your presence, very befittingly. I want to introduce Dr. Dongarra by not narrating his resume or CV for several reasons. One, we will stay here for the next 30 minutes. We don't want to do that. We want to start the talk ASAP. Second, the resume does not indicate many things, which I'm going to mention a few things here. One thing is for sure, well, let me highlight the main accomplishments. He is a fellow of the IEEE, fellow of ACM, fellow of AAAS and SIAM. He is a member of the US Academy of Science and US Academy of Engineering. And he's also a foreign member of British Royal Society. There are a few things which are unique about Dr. Dongarra. One is, and everybody calls him Jack. I hope you don't mind me. One is supercomputing and Jack Dongarra are synonymous. He is the champion. He is a pioneer in the sense that he made supercomputing to mainstream, especially industry usage. And that is not shown on his resume as I'm trying to explain the impact. Needless to say, his papers are more than 1,000. And he told me he lost count, so I don't blame him. Career research funding is in the vicinity of $50 million. For me, I started reading his research paper when I was a graduate student, and I have continued to do that. I have learned a lot from him. Also, as a friend, he's been very supportive. So thank you, Jack. He has some remarkable or insatiable desire to continue to expand knowledge. He has recently become Professor Emeritus, stepping down from his regular position. And he is leaving behind 40+ research assistants, which speaks volumes for his ability to work. The second thing, if you look at the career of Professor Dongarra, is that for most of us, research comes and then we stabilize, we near retirement, but he has continued to grow and expand his output. And that is not just in terms of papers, but in terms of producing actual software which has been used extensively. So he and I also, I was privileged to collaborate with him. We won 3 grants, 2 from NSF, each with $500,000. And it was very great working with him. What are the other things I want to mention? I had 1 or 2 questions. One is, Jack, please tell us if there is any accomplishment left. Well, there is one. The biggest of them all. I am being forgetful. And that is, he's a Turing Award winner, which is equivalent of Nobel Prize in computer science. So after that, are there any accomplishments left? And secondly, what keeps you motivated to reach such levels even when you are stepping down as a regular faculty member? So ladies and gentlemen, please give a very warm welcome to our distinguished speaker, Professor Jack Dongarra.
Well, thank you so much for that kind introduction. I often wonder who that person is. Let's see, I'd like to, well, first I'd like to thank the organizers for allowing me to be here with you today. It's a pleasure to be back on campus. I was here a few years ago, and I guess you weren't celebrating 50 years, but 50 years is quite an accomplishment in computer science. So I'd like to talk about some of that. But I first want to tell you about a few things about myself, I guess, and how I got here. So my family comes from Sicily. So my grandparents were all born in Sicily. They come from 2 small villages in the center of Sicily, Villarosa and Santa Caterina. And they didn't know each other when they were in Sicily. Sicily's a beautiful country. It's mountainous, it's rocky, and you have a sense of isolation when you go see the terrain. My grandfather worked in a sulfur mine in Sicily, and I'm sure that was a hard existence. And he decided that he should do something else. So he got on a boat when he was 42 years old, and he arrived at Ellis Island with his family in 1929. He had $25 in his pocket, and my father, Giuseppe, was 10 years old when he arrived at Ellis Island. My parents had a very basic education. They didn't finish high school. They knew the importance of education, and they pushed myself and my 2 brothers to make sure that we were educated. I excelled in certain subjects like math and science, but I had some trouble with reading and spelling, and later I learned I'm dyslexic. I wanted to be a high school science teacher. That was my ambition. So I enrolled as an undergraduate. I lived in Chicago. I enrolled as an undergraduate in a place that educated the high schools, educated the teachers for the Chicago public school system, basically. It was a normal college. Today it's called Chicago State University. And I wanted to be a science high school teacher. My last semester in college was sort of transformational. I was encouraged to apply as an undergraduate to a program at Argonne National Laboratory. Argonne is a Department of Energy laboratory located in the southwest suburbs of Chicago. And the program I applied to was to spend a semester with a scientist. So I would go and be embedded with 40 other students from around the country and work with somebody. And again, that was really a big transformation. I found my passion in terms of things like computer science, programming, mathematics there. And I remained at Argonne, starting as an undergraduate, going to get a master's degree at the Illinois Institute of Technology, coming back to Argonne and working full-time. And Argonne encouraged me to go and get a PhD. So I went off and went with a friend at the University of New Mexico and got my PhD, worked at Los Alamos while I was getting my PhD, and then transitioned back to Argonne National Laboratory. So I was at Argonne from basically 1973 until 1989. And in 1989, I moved to Tennessee. And I work still today at the University of Tennessee, the other UT perhaps, and, and Oak Ridge National Laboratory, which is a Department of Energy laboratory located just outside of Knoxville. It's an open science laboratory run by the Department of Energy. So that's sort of my story. That's a picture of me at Argonne. That's a 1973 version with a little bit more hair on the top of my head than I do have today. And that's sort of where my story really begins. So in 50 years ago, just as the department is 50 years old, 50 years ago, these were the supercomputers. There were two machines, CDC 7600, was designed by a rather famous computer architect. Seymour Cray was the designer of that machine. And it had a cycle time of 27.5 nanoseconds. The other supercomputer was a machine we had at Argonne National Laboratory. It was an IBM 370-195. And it had a cycle time of 54 nanoseconds. These were sequential machines, right? So a single stream of instructions being executed. But they had a number of very interesting features. The CDC machine had 65 kilowords of memory. So that's what you had to work with in terms of space. And it had a peak performance of 36 megaflops. I'm going to use flops a lot. So flops are floating point operations per second. So flops 64 or 65, 36, thank you. Megaflops is 36 million floating point operations per second. Add or multiply, those are the operations we have. 64-bit operands. That's what we normally do in scientific computing. So that was the supercomputer of the time. Yeah, it broke down occasionally. That was a normal operation. The machine that we had at Argonne had 4 megabytes of primary memory and had a high degree of parallelism. Both machines had a high degree of parallelism in terms of the instruction execution. So they would start an instruction and they would immediately start the next instruction before the first instruction really had a chance to finish, sort of pipelining things along. And they were very advanced machines for their time and produced state-of-the-art computations. There was a need for mathematical software on these machines, matrix computations, and this guy here, Jim Wilkinson, is sort of the father of linear algebra, systems of equations, and eigenvalue problems. He's the guy who came up with a lot of the algorithms, and he As I get further away here, my pointer stops working. He received the Turing Award in 1970. So I had the pleasure of working with him. He's one of my mentors. And we wrote a few papers together. So he created a number of algorithms, and those algorithms were expressed in ALGOL. So ALGOL was the programming language at the time, mainly in Europe. The ALGOL programs were written down in this yellow handbook for linear algebra, and again, it was solving systems of equations. The project I worked on first at Argonne was to translate the ALGOL into Fortran. So it was a translation project. So translating the ALGOL into Fortran, which was the language that was used at the lab, was used for scientific computations. And we produced this book, which was really a translation of those algorithms, trying to make them portable. So portability is a big thing in our software, in our mathematical software. Portability, today we take it almost for granted. But at that time, back then, we had different machines, and those machines had different kinds of arithmetic. So today we have an IEEE standard that defines what the floating point arithmetic is. Back at that time was the Wild West. Each manufacturer had their own way of doing floating point. And to make a program portable that we could take from one machine to another was a challenge in terms of how do you design the code. These algorithms had to converge and produce the correct results, of course, to a working precision, whatever that working precision was on the machines. So that was a translation project, a lot of innovation in terms of the software to make it portable that would run on these wide machines. But it was scalar operations. And this was a translation project. So it translated the ALGOL into Fortran. And if you know something about ALGOL and Fortran, they have different ways of representing arrays. So in ALGOL, the arrays are represented row-wise. So the rows are contiguous that represent a two-dimensional array. In Fortran, the rows are organized by column, going down the column in contiguous fashion. So different organizations that ALGOL was not left unnoticed in the algorithms that were designed by Wilkinson and Reinsch. They respected that row orientation to get a little bit better performance. But in our translation, we ignored it. So the Fortran programs that we developed were particularly poor in terms of performance because they accessed things in the wrong way in which it was stored. One thing you should go away with is the most expensive part of doing computations, it's referencing data. So memory access is very expensive on all machines, and that caused a lot of performance issues. So IcePack was innovative, it was portable, but the performance was rather poor because of that. The next decade brought along a number of other supercomputers. These machines were quite different in terms of their architecture. These were vector computers. So there was a vector instruction that was issued, and that vector worked on a stream of data. There was a machine that was made by a company called Cray after its founder Seymour Cray. That machine was quite popular in terms of scientific computations. There was another vector computer called the CDC Star 100 made by Control Data Corporation. Again, another vector architecture. There was a major distinction between those vector machines. Again, you would issue a vector instruction and it would have an effect across an array of numbers, say multiplying two vectors together or doing a sum dot product of those vectors. Those are the basic operations, let's say, for these machines. The Cray architecture had a set of registers where data was contained. You would move data from memory into the registers and then do the vector operations out of those registers. The CDC Star had an architecture which streamed data from memory into the part of the machine that does the operations and then streams the data back out into memory. As I just mentioned, data movement is the most expensive part. If we're moving data from registers, it's fairly inexpensive. If we're moving data from main memory, it's very expensive. So this architecture that was in the CDC Star 100 was not as efficient as the architecture that Seymour Cray envisioned with his vector architecture. And they had performance levels. The Cray was 160 megaflops, 160 million floating point operations per second. And the CDC star was comparable, about 100 megaflops. And again, did those memory-to-memory operations. The Cray 1 sold about 100 machines, which was really quite successful for a supercomputer at that time. The CDC star had nowhere near that kind of popularity. We were trying to develop software which was portable, and an important aspect of that is getting the basic operations to be defined as a call to a subprogram. And then we would expect the manufacturer to implement that subprogram very efficiently on their architecture. And we came up with, the community actually came up with something called the level 1 BLAs, basic linear algebra subprograms. And those level 1 BLAs did vector operations. So we had some vector operations we were defining as kernels, and then we would build software on top of those vector operations. And that basically was not the way that this package for solving eigenvalues, IcePack, was constructed, but we knew that we had to organize the data in a way in Fortran so we can access things by column. So we were engaged in a process of doing that, and that package was called Linpack. So Linpack is a package of mathematical software for solving systems of linear equations that organize things around these level 1 BLAs, these vector operations, and organized it so they would be very efficient. Because it was Fortran, it was organized by columns. This is a picture of the guys who did Linpack. This is Jim Bunch from the University of California, San Diego, Pete Stewart from the University of Maryland. This is Cleve Moeller from the University of New Mexico, and that's the 1979 version of me with, again, a little bit more hair. This is my car, by the way. This is my license plate. It said Linpack. And this was the user's guide that we generated back at that time. Cleve Moeller, you may not know Cleve's name, but you may know what he did. He formed a company, and that company made a product called MATLAB. So MATLAB is the product that Cleve created. He was also my advisor. So in the appendix of this Linpack user's guide, I put together a table. I had access to a number of computers, and I wanted to show the performance of solving a system of linear equation on these machines and give guidelines as to how long it would take and extrapolate to larger matrices so a person could see how long it might take on their particular architecture. And that table is reproduced here. This appeared as an appendix. It listed about a number of machines. I can't remember the exact number, but about 20 machines there, ranging from a Cray 1 down to a machine, a PDP DEC machine, which was very low performance. But the performance levels are noted here, scratched in pencil. The machine at the National Center for Atmospheric Research that had the Cray 1 was at 14 megaflops. So that was the performance it achieved for solving a system of linear equations. I maintained this list of machines for solving a system of linear equations. So the test basically is solve AX equal B. I'm going to give you a matrix and a right-hand side. You have to solve that problem using Gaussian elimination with partial pivoting. You have to use 64-bit precision, and I'm going to check your answer. So that was the benchmark that evolved from this appendix, and that benchmark grew. So this list of about 20 machines grew to 100 machines, it grew to 500 machines, it grew to thousands of machines. And when we had people come to Argonne with a new computer they were trying to sell us, I would point to this list and I'd say, where do you fit? And they would project something, and then we would run the program. And the program running was most likely less than what they projected in terms of what they thought their machine would produce. So that list became important and has a life of its own today, and I'll get to that as we go on. So in the 90s, there were changes to the architecture. We had cache-based systems. We were starting to see parallel processing in the machines that were available to us. There were a number of commercial companies that were created that used this architecture: shared memory, cache-based systems, parallel processing going on at that level. And the companies are companies such as Multiflow, Alliant, Convex, Kendall Square, Sequent. They all had products, all independent companies that sprang up to try to produce something that was a mini supercomputer. Those companies had a modest amount of success. Today, all of those companies are out of business. So they're all, I'll call them failed, although they generated a lot of interest, excitement. They educated people in terms of doing parallel processing in a shared memory context. Going on with the story, we were developing software, and we knew that we had cache-based systems. So cache allows one to get easy access to the data that's there in terms of time, the movement of data. And we were trying to develop algorithms that would exercise and use that feature, but we needed some standards to do that. Again, we wanted standards that would allow us to do not just vector operations, but higher level of description. So we created something called the level 2 and the level 3 BLAS operations, basic linear algebra subprograms, to do matrix vector and to do matrix operations. So this was a community effort. There was a small group of people that developed what I'll call the standard, and the community had input into what should be extra included in that set of routines, so we would be able to feed off of the community and build a standard that really had input from a wide range of applications. And that's exactly what happened. So we took the ideas and algorithms in IcePack, the eigenvalue stuff, and Linpack, the systems of linear equations, and we decided to create a new package, and that package was called LAPack. So LAPack takes eigenvalues and systems of equations, uses these higher level BLAS operations to accomplish them, raising the level of granularity, trying to get to higher levels of performance. And a group of us produced that software. So this is the group of people who created LAPack. That's my car. It has a license plate which says LAPack, of course. And we did that, and that package is in wide use today, replacing basically the software that was in these two packages, creating a higher level. The advances in architecture continued. We went from shared memory to distributed memory architectures. So shared memory says that all the processors have equal access to the data that's in memory. They have a single unified global address space. With distributed memory, each of the processors has their own memory. And in order to exchange data and perhaps synchronize, you have to send messages. So you pack up a message and send it from one process to another, then do the operations and perhaps broadcast that information to all the other processors. So that was the model of computing that we had. And again, a number of companies sprang up to create machines in this space. And those companies are listed here, companies like BBN, Mirius, Thinking Machines, Mako, NQ. They all had architectures that existed in this domain. All of those companies had a brief period of existence, and then they all went out of business. They couldn't sustain it. They couldn't really have a market for those products. But again, a lot of people were educated. The ideas created many new creations in terms of how they do business. But one thing we were missing was a standard for passing messages. Each of those vendors had their own way of sending messages. They all had their own library for message passing. And that led to chaos in terms of having portable programs. So we got the community together and created something called the Message Passing Interface, MPI. So about 40 people got together at a hotel actually close by here, close to the Dallas-Fort Worth airport. We got together every 6 weeks to create the standard, to develop the ideas, and to mature them, and to get buy-in from the companies. So at the end of a year and a half, after meeting every 6 weeks at a hotel at the outskirts of the airport, we created MPI. So that was the first message passing interface. It was immediately embraced by the manufacturers, and we had a standard on which we could build parallel scientific programs. That led to the creation now of libraries that we could build on those ideas. LAPAC was really designed for shared memory machines, which had cache-based architectures. We wanted to take those ideas and move them to do message passing, to allow a set of programs that would do message passing on the architectures that were available to us. So we used MPI as the parallel mechanism for that, and we created a programming system for solving systems of equations and eigenvalue problems that's called ScalaPack, for Scalable LAPAC, which does message passing under the covers in a portable way so it can be moved from one machine to another and used without too much effort on the scientific programmer's part in making those programs active for solving eigenvalue problems and systems of linear equations. About this time, the architectures continued to evolve. We had multi-core systems that were hybrid. Multi-core in the sense that we have one chip that has multiple processors on it. Those are called cores. And hybrid in the sense that we added to the mix a GPU. So we had a graphic processing unit attached to that chip. The graphic processing unit was capable of doing a lot better in terms of floating point operations. And the basic mode of operation here is the chip itself, the multi-core chip is in charge. He passes information over to that GPU. The GPU does the operations and then passes the information back to the multi-core processor. So it's a multi-phase kind of operation. The GPU can do much, much greater in terms of performance, and the CPUs are there really to just orchestrate the data movement between the GPU and the CPUs themselves. So we created a package around that architecture, and that package is called Plasma. Again, a system of linear equations built on top of standards, targeting specifically multi-core and GPU kinds of architectures, using a slightly different mechanism to exploit parallelism. Our machines now are getting larger in terms of the number of processes that you can run, and a standard way of doing parallel processing at that time was to just run loops in parallel. So you do a fork join. You fork off a number of things that you do in parallel, and then you join back together again to create a single thread of execution. Then you move on to the next phase of the iteration. So that model of parallelism is fine if you have a small number of processes. If you have lots of processes, think now thousands, tens of thousands, today we have millions, you can't do that. It's that join part that really creates a bottleneck and really causes performance issues for programs. So we were looking for different ways of expressing programs. And pulling out of our bag from computer science, we decided on looking at directed acyclic graphs. So we're going to express our algorithms not in terms of loop level parallelism, but in terms of a data structure, a data flow kind of architecture that results from a directed acyclic graph. So we have nodes, and think of those nodes as fairly large chunks of computation, and think of the arcs as being dependencies from one node to another. And when all of the dependencies are satisfied, a node can execute, can pass information, and then when it finishes, it passes forward its information about what's going on. So the DAG was embraced as a way to get around that fork join level of parallelism. If you follow the critical path in the DAG, you'll express the most parallelism you can, and that's what we're looking for. Look for the critical path, the longest path in this graph, execute it first, and then it will release the most levels of parallelism. So our algorithms were evolving to that level. We also decided to create something called a batched set of BLAs. In scientific computations, we don't usually have one kind of operation like a matrix multiply. We have many matrix multiplies that we want to do at the same time on different data. So we wanted to have one routine that we can call, and in that one routine, do all of those matrix multiplies in parallel. And that would be done presumably on a GPU and be done very efficiently, keeping the GPU very active throughout the course of that operation. And not just matrix multiply, but many kinds of higher level operations we were able to express in that same way. So, so that became a standard which the community embraced as well. So we have a progression here of software projects from things in the early 70s down to things that we're seeing really today in our programming model for expressing things using a high level of parallelism. The architectures continue to evolve. So today we have hybrid architectures using CPUs and GPUs. We have multiple GPUs now being associated with those multi-core processors. And we have a machine like a machine at Oak Ridge National Lab called Summit. It has a peak performance of 200 petaflops. So that's 200 times 10 to the 15 operations per second. So that's what its theoretical performance level is. And the machine is fairly large. Think of it as the footprint the size of 2 tennis courts. It takes 10 megawatts of power to run this machine. So what's a megawatt? If you use a megawatt for 1 year at your house, you're going to get a bill from the electric company for $1 million. So a megawatt year is about $1 million. So this machine, the Summit machine, costs about $10 million a year just to turn it on. So the machine itself cost about $300 million in terms of the price of the machine. And again, it's a fairly large machine. That's not the current state of the art. That's the machine previous state of the art, let's call it. Well, architectures continue to evolve. The software continues to match the architecture. So we have a project today called Slate. Slate is a software project for dealing with matrix problems, systems of linear equations, and eigenvalue problems. It's written in C++. It uses this DAG notion to express parallelism. It is able to work with a heterogeneous collection of nodes, and it's sort of targeted for machines that have on the order of tens of millions of cores, where some of those cores are devoted to GPU execution. So we're trying to develop software that can address this pyramid of computational devices, from these big machines that we would call our supercomputer centers, down to regional machines, down to clusters, down even to laptops. So our software will run across that whole range and presumably do it in a fashion where we can extract high levels of performance, have portability, be able to have readable software, to have accommodate for the most accurate algorithms, and provide something which really has community involvement in terms of how that software evolves over the future. So today, we have these highly parallel machines. They have distributed memory. They use MPI for communication between nodes. They use OpenMP as the programming paradigm within a node. That's a shared memory paradigm. The biggest machine is a machine called Frontier, and that machine has a peak performance of 2 exaflops. So an exaflop is 10 to the 18 floating point operations per second. 10 to the 18. That's an incredible number. I have a hard time getting my head around that number, and I'll describe that in a little bit more. It's based on AMD processors, AMD chips, multi-core, and an AMD accelerator, GPU. So that's how the machine is constructed. Each node has 2 of these AMD chips, multi-core chips, and 4 AMD GPUs. And the performance, those 2 exaflops, 98% of the performance comes from the GPUs. So you had better be engaged in that GPU parallel performance programming in order to extract any kind of performance on these machines. The machines are based on commodity processors and commodity accelerators. This idea of simple loop-level parallelism is not going to work when we have a machine that has on the order of 8 million cores in it. So you have to do something different. And this notion of expressing things in terms of a directed acyclic graph is a reasonable way to exploit that kind of performance. Communication is very expensive. These machines are over-provisioned for floating point operations. There's too much floating point capability. It's really the communication that's going to kill the performance. And the traditional notion is if I have two algorithms that do the same thing, I was taught if we take a look at the operations, the number of operations that they do, I can determine which one's going to be better. The one that does fewer operations is going to be better in terms of the performance. That's not true today because we have to take into account the communication that the algorithms do. Algorithms that do more communication are going to be more expensive, even though they may do less work over the other one. So that's a new notion. And today, in the past, we thought about doing scientific computations using 64-bit floating point accuracy, maybe 32-bit single precision. But our hardware today comes with 64, 32, 16-bit floating point operations, and even 8-bit floating point operations. 8-bit and the 16-bit operations are there not for us, not for the scientific community that does very traditional kinds of computations. They're there for machine learning. So machine learning can get by with much shorter precision in terms of the algorithms that are used for the training of machine learning, and that's why our architectures today have 16-bit and 8-bit floating point. I maintain this list of the Linpack benchmark, solving a system of linear equations looking at the time. I've done that since 1978. My colleague Hans Moyer and Eric Strohmeyer, they had a list of the fastest computers. And they were listed just by the theoretical peak performance. And Hans approached me and said, why don't we get together and create a list? We're going to call it the top 500, which uses your benchmark, solving a system of linear equations, and ranking the machines based on solving that system of linear equations. So that's how the top 500 was created. We're going to rank the top 500 fastest machines, and that list is going to come out twice a year. And it solves that system of linear equations. The algorithm is Gaussian elimination with partial pivoting. You have to use 64-bit precision to get the correct answer. And typically, as you increase the size of the problem, the performance level rises until you get to some asymptotic point. And that's what we're trying to capture with the top 500 list, that asymptotic point. So this is a look at supercomputing going back to 1993 when we started the list. So the red dot is listing the machine at number 1 position, the fastest supercomputer. So today, the fastest supercomputer is at 1.19 exaflops, 1.19 times 10 to the 18 floating point operations. That's the rate of execution for solving that benchmark. Back in 1993, the benchmark was solved around 60 gigaflops, 60 billion operations per second. The blue line is charting things at the bottom of the list. So that's the number that's the machine that just made it on the list, number 500. So you can sort of see where things have gone, where things have been over the past. That sort of brackets what I would consider a supercomputer. We see some funny business going on here. I put in some trend lines so you can see the difference between that. So back here, we had a number of things happen that could cause that trend line to change. One thing is Moore's law is slowing down. It's not ending, it's slowing down. So the number of gates on a chip are not maintaining the pace of doubling every 18 months. The other thing that happened around this time is Dongarra scaling ended. So Dongarra scaling is this ability to develop chips which had smaller feature size, had the ability to use smaller voltages, had less power going into it, and had higher frequencies. And that ended around 2007 because of voltage leakage. And that voltage leakage caused the chip to heat up, So today we're frozen in terms of cycle time around 3.5 gigahertz. So our processors are sort of stuck at that point unless you want to engage in special cooling to go beyond that. Our chips are running about 100 watts today. Our chips that we would have in our supercomputers, about 100 watts per chip. And if you increase the frequency, things happen which makes that 100 watts go up rather dramatically, and I'll have more to say about that tonight. So that sort of brackets supercomputing. Back in 1993, the fastest computer so this arrow is actually in the wrong place. So think of this arrow is right there. So the fastest supercomputer was a Thinking Machines. It was the #1 computer. It ran at 60 gigaflops. That was the performance level for that computer. So today, my laptop, this machine here, I can run the benchmark on it. And when I run the benchmark, I get 426 gigaflops. So that's stunning achievement that's occurred in a very short period of time. So this is a machine that was used for nuclear weapons computations, right? It cost hundreds of millions of dollars to put in place. It consumed, megawatts of power, and today I have something which I use on an airplane for about 12 hours and use mainly, to be honest, to read email. So it's an incredible, incredible change, and that would have been one of the fastest computers not too long ago. So that's a stunning achievement, I would say. This is a list of the top 10 computers. I'm not going to go through the whole list, but I just want to point out the #1 machine is at the Department of Energy Laboratory, Oak Ridge National Lab. It's called Frontier. HPE is the integrator. So they are the guys who integrate parts. They don't make chips. They take chips and they put them together. And the chips are made by AMD. They have an AMD multi-core and an AMD accelerator. They use an interconnect that comes from Cray, that company that had the fastest computer way back when. The legacy is they now make interconnects. And that machine has 8.6 million cores in it. So if you're going to use this machine at scale, and this machine is intended to be used at scale, you have to orchestrate 8.6 million cores in your program. It has performance on the benchmark of just over 1 exaflop. That's 71% of the theoretical peak performance. So the theoretical peak is paper and pencil calculation. How many cores, what's the cycle time, how many operations do you do per cycle, multiply all that together, and you get the theoretical peak. And this machine, for this problem, is achieving 71% of that theoretical peak. The power consumption is at 22 megawatts. Again, $22 million to turn it on for a year. The machine costs $600 million. So just to put that in perspective. And this is a measurement of the efficiency. 52 gigaflops per watt. You want that number to be as high as possible. So the red things here indicate GPUs. So all the top 10 except for one use GPUs to accelerate the performance. This machine is a machine in Japan. It uses an ARM processor, which they've extended to use vectors. So it gets its boost by using vector operations. And it does a pretty good job of that. It gets 82% of its theoretical peak performance. So the US has 5 machines in the top 10. Japan has 1, Finland has 1, Italy has 1, and China has 2 machines in the top 10 list. So again, exaflop is 1 floating point operation. Add or multiply is a flop. Exaflop is a billion floating point operations per second. I gave this slide from this talk at a conference a few months ago, and I said a billion. And there was a newspaper guy in the audience, and he interviewed me afterwards. And again, I said a billion. And when I read his story, it said 2 billion. It's not 2 billion, it's a billion, okay? So just so we go away with that notion. So a billion floating point operations per second. So if each person on Earth did 1 operation per second, each person on Earth 1 operation per second, it would take 4 years to reach an exaflop. And that's what this machine does in 1 second. Just trying to put that in perspective. So in China, there's rumored to be 2 or 3 exaflop systems. But they haven't come forward. They haven't disclosed those machines. They disclose them by running the benchmark and sending me the results. So they decided they don't want to do that. So why would they not send the results? We know the machines exist, and I know from third party that they're running above exaflop. Well, there's a geopolitical reason. China's afraid that the US would impose more restrictions on technology going to China as a result of that. So China has slowed down the submissions to the top 500 list. So back in 2020, last year, they had the most supercomputers. China had the most supercomputers. US had the second most. And because of China's not reporting, the US now has more supercomputers on the list. China, however, still produces the most supercomputers. They make the most supercomputers, right? And they sell them internally, but they also sell them around the world. They sell them in the US. So Lenovo is an example of a Chinese company selling machines here in the US. Supercomputers, as well as INSPER, Sugan, NUDT, the National University for Defense Technology, Huawei, and a few others. Okay, the US Department of Energy is heavily invested in scientific computing. Science is driven by computation, by simulation today. So they invest in supercomputers. So they've invested $4 billion over the past 7 years. $4 billion. So what do you get for $4 billion? You get 3 supercomputers, right? So you get each of them $600 million. And we have one machine at Oak Ridge called Frontier. There's a second machine going into Argonne National Laboratory outside of Chicago. It's being installed today. It has Intel parts, Intel multi-core, Intel GPU. And there's a third machine that's going into Lawrence Livermore National Laboratory, which would be similar to the Oak Ridge architecture, just updated with the newest processors. You also get 21 applications. This is the whole point of this program, called the exascale computing program. There are applications that need high-performance computing to advance their science. And these applications are things like wind energy, all energy-related. So accelerators, materials, things like, I can't quite read it, chemistry, you can see the list there, but there's 21 that have been identified as applications that need these high-performance machines, and you get a bunch of software. So basically the money was split between hardware applications and the software. So the applications and software got about a fourth of the money, I'll say, from this project. This project is about to end. It's going to end at the end of this year. So about 3 months left, 2.5 months, and the project ends. And the thing that's frightening is there are 800 people in the Department of Energy and at universities working on this project, and there's no follow-on. So these people are scrambling right now to find funding so they can carry on. I find it to be an incredible situation in the Department of Energy, and given the state of our government in terms of allocating and appropriating funds today, I think it's going to be a bad time for the computational scientists who are working at the national laboratories and who will leave the labs and find jobs easily in industry. So this performance and benchmarking, I've been doing it for a long time. This Linpack benchmark is a long-standing benchmark, started in 1979. A lot of positive features. It's easy to understand, easy to run. It shows trends. However, much has changed since 1979. The hardware has changed considerably. Arithmetic was expensive back in 1979. Today, our machines are over-provisioned. So we have too much capability for floating point operations, and data movement is really the expensive part. So the Linpack benchmark does not do a very good job of imitating today what real applications do. So we need more benchmarks. We need to be able to follow what the real applications are doing and to track the performance for our systems. So if you design a system that gets a good Linpack number, that's going to be a poor machine in terms of actually using it to solve scientific problems. So today, our problems really, our large-scale scientific problems comes about by looking at three-dimensional partial differential equations, discretizing those differential equations, coming up with, again, a system of linear equations that needs to be solved, but this time the matrix is large and sparse. So we want to come up with a benchmark that really tests that kind of problem and to see what kind of performance we get on that problem itself. So we designed a benchmark called HPCG. It's the other benchmark. It tries to imitate a large-scale three-dimensional partial differential equation. We're taking this 27-point stencil. It generates a matrix which looks something like this. It's large, it's sparse, it has structure associated with it. And the idea is to solve that problem and look at the performance on the machines. So this is what that benchmark looks like. So the number one machine is a machine from Japan called Fugaku. That was the number two machine on the other benchmark. It had a performance, well, let me just unveil that. This is the performance for doing Linpack in terms of petaflops, 442 it achieved. And for this new benchmark, it gets 16 petaflops. And I've indicated here what the fraction of peak performance is. So when you take a look at that, the fraction of peak performance that we get out of one of the better machines is 3%. So we're getting 3% of the theoretical peak performance. And look at what it is for the number two machine here, Frontier. We're getting 0.8% of the theoretical peak performance for this problem, which is more characteristic of what is really being run on this machine. So the architecture is really not suited for the kinds of problems that they want to run. And that I think is a failing of our machines and how we acquire machines. So think about a race car that has the potential for going, I don't know, 200 miles per hour, and think about that car running less than 2 miles per hour. Right? You'd be pretty disappointed with that race car if you got around 1% of its peak performance. Please.
To be fair, I think people who have been running the Linpack, they have worked for years. This HPCG is optimized version or just a...
It's an optimized version, so people have worked very hard to get the performance up. And that's the performance that we see, 0.8%. Again, message passing is really killing the performance on these machines. That's the bottom line. We can't do this algorithm doesn't lend itself to doing matrix operations. Our machines are designed really to do matrix operations. Okay, so let me conclude here and say that the hardware is constantly changing, going from scalar to vector, to distributed memory, to accelerators, to multi-precision. We see three really computer revolutions in terms of high-performance computing, deep learning, which I didn't have time to talk about, and edge computing, as well as artificial intelligence. The algorithms and software really follow the hardware. So the picture that I have for this scenario is we have a certain amount of money that we want to buy a supercomputer. And we tell the manufacturer we have to get this performance. So the manufacturer goes away and designs a machine, cobbles it together, which has a theoretical performance that hits that mark that we asked for with that budget that we gave it. And in order to do that, they use commodity processors, commodity CPUs and commodity GPUs. And they throw them together in a box. And they take that box and they throw it over the fence. And the algorithm guys and the software people have to now fix their methods on this machine that was thrown over the fence. And we do that. It takes us about 4 or 5 years, and we do a pretty good job. And then another machine gets thrown over the fence, because that machine we throw away, because it's outdated at that point. And that's the cycle that we're in. So there's a good paper that was written, interesting paper that was written in Science a few years ago. The paper says there's plenty of room at the top, what will drive computer performance after Moore's law. They talk about, this is Charles Lyserson and a few of his colleagues, they talk about the challenges for software, for algorithms on the hardware that we have. The title is a riff on Feynman's lecture back in 1959, where he's talking about quantum computing, and he talks about there's plenty of room at the bottom for that design. So thank you very much for your attention. I'd be happy to answer any questions that you might have.